Welcome to the lecture on heuristic searches for CSCV 471 at the University of Arizona. So this is Greg Wagner, and I'm going to go over heuristic searches. And heuristic searches are basically finding the best way to a path given a cost function. Now, what we did before the previous lecture called blind searches is there was basically no cost to the path you'd go. So sometimes you get a path from the initial state to the goal without actually doing the best path. So what heuristic searches try to do is do the best path, and what they do for that is add in a cost function that basically, if you try to take the path that's the least best way to do it, the cost will go up, and you try to minimize the cost function. So, in other words, a blind or uninformed strategies basically don't use any information. They kind of just say, okay, I know where I'm going. I mean, I don't know where I'm going, but I'll find a way to get there as long as I don't go back. Whereas a heuristic search basically associates a value with each state or each node, finding the best possible, trying to find the best possible way to get to something. So you can also think of these as we have depth first searches and breadth first searches. You can think of these as best first searches. So you define a node function, basically define a function where we have the node and we get a real number of function f of n. And we call this evaluation function, whose basically the value is on the contents and basically the goodness of the state associated with the node n. And then we basically order the nodes and the fringes in increasing values. So remember with the breadth first search, we put the new fringes in the back of the queue, and with depth first searches, we put the queue, we put the fringes in the front of the fringe queue. With best first searches, we basically we order the nodes in increasing values. Basically, the best scores we search first. And then basically, kind of the deal with heuristic functions is finding a good evaluation function. And so basically for this lecture, we'll go over a few different evaluation function techniques. And so to define the informed search, we add basically domain-specific information. So for a maze, basically, are we getting closer or further away from the targeted number of steps? And then so we have this function, the heuristic function, h of n, that estimates the goodness of a node. So specifically, h of n is the estimated cost, basically the minimal, the estimated cost of going a particular route. And so we don't have, unless we have all information, the heuristic function is just an estimate based on the domain that we're in. So for example, if you're doing using Waze or Google Maps to find the directions, you'll try to find a direction that basically has the least amount of time or least distance traveled as far as the heuristic function, but it may not have all the information. So maybe there's some traffic that just came up because of an accident. It doesn't have that information, but it'll try its best to find the quickest path between 2 points. And that's what most searches try to do in this case. So the heuristic function, h of n, is the cost of the cheapest path from the node n, so the current node you're in, to the goal node. So for the 8 puzzle, h of n is the number of misplaced tiles. So the number of misplaced tiles in this case is 6. So the only tiles that are in the right places are 4 and 7. So 5, 8, 2, 1, 3, and 6 are the 6 misplaced tiles. So what we want to do is minimize this h of n number. So in this case, all the numbers are in order. So what would the h of n for this be? It would be 0 since all the tiles are in the right place. And so for the heuristic function, we want to just try to estimate the cost. So we have to give it some sort of score. And so maybe a better way of calculating the h of n, instead of doing the number of misplaced tiles, is doing the distance between the tiles. So maybe this is a better estimate of how we're going to do. So in this case, the sum of the distances every tile has to go. So we're going to go from top left to bottom right. So 5 is going to go from here to here. So it has 1, 2 spaces. This is equivalent to 2. 8 needs to move down from 1 to 3 to here. So that's why it's 3. 4 is in the right place, so it's 0. 2 just needs to move up 1, so that's why it's 1. 3 needs to go from 1 to 3 to this spot. So 3, so again, 7's on the right spot. And then 3, and then I just did 3, and then 6 just needs to move up 1 up spot. So using this estimation, we have a h of n of 13. And so what do you think would be the better one for this? I would think the better one for this would be h of n this, because it gives you kind of a better score of how far things have to travel. So, but basically the point being is, for these two examples, using the different, is you have to come up with a score and you try to find a way of calculating the h of n function, the heuristic function, that could make your searches the fastest or the best. And then, so for create the evaluation function, which is f of n, would be the where g of n is the cost of the best path found so far between the initial nodes. So as you go each step, basically g of n is going to increase, and h of n should go down as you get closer to the goal state. And so in this case, we're not like counting the number of steps we're going to take. We're just basically trying to find the best path. Whereas we add this g of n cost function, we're also counting the cost of each step. So to give you an example, so in this case we're using h of n, the number of misplaced tiles. So in this case we have 4. So if we do each of these 1 steps, so in this case we're basically moving the green one to here. So the white spot's the missing one. Or we could do moving the blue one down. So this one has basically 3 misplaced ones, and then we can move it the other one. So basically with this blue thing, we basically only have 3 steps. So in this case we have the best one step forward is 3. And then so we're going to ignore the other paths. We're going to go down this path, and we see a 1, 3, 1 of 4, 3, and 1 of 4. And then since we're going to go down, we're adding to our fringe this one, so we're going to go down this path. This is the best path. We see that we have a 3, and then basically we get stops. We're at this 4 where it gets worse. So as your score gets worse, you want to turn around. So now we're going to come back up this path and go down the 4, and see that the 4 here, the worst case here is 4 and 4 here. So we're going to skip this. We're going to go down this path, and we see a 2. That's less than the h of n of 4. So we're down this path. We see that it's a 1, so we only have 1 more step to go. And then we get to another step where we have 1 of 0, where we're in a goal state, and 1 of 2. So we can see that this is a path, and we're pruning as we're going through. We're seeing, okay, this path isn't going to work. We're going to go down this one. So we order it in best paths, and then if the h of n gets worse, we stop and then we backtrack. So in this case, we're also going to have add a step cost function, the h of g. So the initial step, we only have 4. So in the next step, we're going to add 1, and then we see that the g of n gets 1, and we see, okay, we got 1 plus 3 here. So this is 6, 6, and 4, so we're going to go down this path. And we see we have 2 cases of 5, and then 1 of 4, so we're going to ignore this one. And we see we have 1 of 6, so it got worse, and then 1 of 7. So in this case, since it got worse here than the path we had up 1 step above, this is worse. So if you notice here, we went down this path, but adding the step cost function basically means we're going to save a few steps. So we go down this path. We see that we're in the 3rd step. We see that it's 5 and 7. So this one's the same. So we're going to go down so this one's 7. This one's 5. This is the same as this one. So we didn't save anything, but we didn't get worse. We're down this path. We see that the number is 4 is the same as 5. And then finally, we get to 5 plus 0. So in this case, this is the best path when we reach our goal state. And then so again, notice how since this step is worse than this one, we didn't actually have to calculate these, and we saved a couple of steps. And then so now we're going to sum up the distances of the goal. So we're going to use that final function. So we have 5. So we have 6, 4, and 4. So in this case, we have 5 again, 3 and 5. So basically, notice what we're showing here is how we're just doing a different cost. This was the sum of the distance of the tile. So that's the second example I showed. And then so we have this one. So we have basically the score of 2. and then we only have one misplaced one, and then we have a score of 0. So this path basically shows, okay, we are ordering stuff on the least number of steps again, but that we don't have a g of n step function. So basically just to show that there's a bunch of different ways to do this. And then notice again here, we're not even going down this path because we see that it's not really pushing us towards our goal. Notice here the sum of the distances basically says are we getting closer to our goals or not. So for a robot function, before you move on, how would you think that we would score each of these boxes? Think of each of these boxes as a node. So one way to score them is use the Manhattan distance. So it's the distance from the goal. So we know, and Manhattan distance is basically L of 1. So basically, it's each step this way. So each of these paths will be 1, 2, 3, 4, 5, 6, 7, 8, and then the closest distance. So this is 1, 2, 3, 4, 5, 6, 7. Notice here how it gets worse as we go up, but that's because we can't walk through these walls. So with the robot navigation, use the Manhattan distance as the function. So Manhattan distance would basically be, again, would be just, you have to kind of step either way. Euclidean distance would be a direct path, but we can't do that for this particular one. Remember, for the robot function, you can only step up, right, down, or left. So we're going to start at 7. And then we see, okay, we got 6, so 7, so this is going down, which is good. And then it goes up, but both these numbers are the same. So we're going to keep on going. And then we see, oh, this is 6. So we're going to go down this path. 5, 4, 3, 2, 1, 3, 4, 5, 6, 7, 5, 4, 3, 2, 1. And then this path, basically this 8 number here kind of hurts us because the path here. So this would be an example where we need to use the step function. And so what happened again, if you back up, is notice how the score of this node is 8, and all these other scores are lower, whereas clearly if you look at it, this path is the quickest. So if we do a greedy search, so this is an example of a greedy search here. Where it doesn't count for a account for a step function as far as the G and N of the example, and so is this complete? Is it optimal? It's complete. Yeah, we'll find a path to it. Is it optimal? No, it's not. And so for a more informed search, we want to add the cost function to it. And so you can also count the number of steps that we're taking as the best overall path. So again, we're going to do this. Now notice how at the origin we're at 7 plus 0. We go into the next step. So we have 7 plus 0 is 7. 6 plus 7 is 7. So these are the same. 8 plus 1. So this is not a good path to go down. Okay, then we see, okay, we're going to go down best first. So we're going to start with this fringe. 7 plus 2 is 9. And so we're going to go back this way. 7 plus 2 is 9. So they're the same. I'm going to go 8 plus 3, so that's 11. 7 plus 3 is 9. 5 plus 4 is 9. 5 plus 4 is 9 again. So we're trying to, remember, when the number gets less than it's 11 here, then we go back. And so this is 7 plus 2 is 9. Now it's 8 plus 3. So now we're getting to steps where it's worse. So now we're going to go back here. We see this, okay, this is 9 again. This is not a path we want to take, it's a dead end. Okay, now we see 7 plus 4, that's 11. So we have 11, 11 here, so we're at the same. 6 plus 5 is 11. And it's going to go down like both these paths. These are both 11, so it's whatever one it gets to first. And it says, okay, 5 went down this one, so it's going to say 5 plus 4 is 11. This is 11 here, this is 11 here. And it says, okay, 11 plus 3 plus 8 is 11 again. And it's going to say 2 plus 9 is 11. And it's going to stop here because 3 plus 10 is 13. So the number of steps for this one's 10. And this one says okay, 3 plus 8, so it's going to go down back this path. It says 2 plus 9 is 11, so it's at least the same as this one. And this one's 2 plus 11 is 11, and then it gets here, 11. So it's going to say the best path is from here down to here. And so what it's doing is we have this cost function, so every step we take is increasing the performance. And then looks like I copied. And then for the admissible heuristic, h star of n would be the cost of the optimal path to the goal. So what we're trying to do is find the best h of n. And so what we're trying to do is trying to find an h of n that's greater than 0, greater than or equal to 0, but less than the heuristic function. So if we know what if we calculate the optimal, so if we have basically what this is saying, if you have multiple paths, your optimal one is going to be the one that's going to be less than the heuristic function. And usually the admissible heuristic is usually optimistic, meaning it's kind of just a general guess that's a little bit on the light side. And then so the function we're going to really go into now is the A star search. So the evaluation function is f of n, where we have g of n as the cost function, h of n as the heuristic function. And so this is basically the cost of the best path so far. So at this step we're going to go, and then h of n is the admissible heuristic. So it's basically the best case. And so this is a best first search with a modified search algorithm. So it's basically using the h star kind of heuristic search. So in this case, to go to every star, h1 is the number of misplaced tiles of 6 is admissible. So basically we're saying the number of misplaced tiles we have is 6, which is our best case. This is the case we're at right now. And then h2 is the sum of the distances. So we have two heuristic functions. One is the number of misplaced tiles, and one is the sum of the distances. And so 13 is admissible in this case. So basically it's saying whatever one we are using is the best case. So what we want to do is find a case where performance doesn't get any worse. And so we're going to come up with a cost function for this robot function. Basically, if you're going along the cardinal edges, north, east, south, and west, we have a step of 1. If we're going to do a diagonal, we're basically doing the square root of 2. So we're doing basically trig, the distance of a 1 unit between diagonally. And so h of n, the straight line distance to the goal, is admissible. So basically the straight line function would be considered the best, the admissible one. So we want to see if we can do better than that. And so for completeness, basically there's a claim if there's a path from the initial goal node A star with no removable repeated states, terminating by the fifth best is both complete and optimal. And basically each step has a number of successors. And then your heuristic function is admissible, then A is optimal. So basically it's saying if h of n is better than your requirements, your claim, then it's going to be an optimal function. And then so assuming that the suboptimal goal G2 is tested by the algorithm, hence a suboptimal goal is G2 is tested by the algorithm. So a suboptimal goal is if G1 is worse than G2. So basically we're going to find a bunch of different kind of distant ways to get to our point, and then we just keep on, whatever one's the best has the least amount of cost is going to be our optimal one. So in this case we have f equals G1, so this is, we're still not assuming, so f of G1 is equal to G, so it's the number of steps. F of G2 is the number of steps. And then we have this node here, so we have a node step. And so in this case, f of n is gn plus gn is less than equal to gn. So basically what this is saying is if this step is, since this step is less than gn plus the h star, this is the best path to our goal. So it's basically saying going to G1 is a better path than going to G2. It's saying the best path to get to the goal. So basically saying if we have multiple goals, a suboptimal one is if we take a path that's not optimal. And then in this case, basically it's saying here, G2 is, we can't basically get to this path from G2. And so it's saying that in this case, G2 is, so we'll say this is optimal, but G2 is actually a better way to get to it. So in this case, G2 would be better. And so using this algorithm, we have the number of misplaced tiles. And so this one would be, in this case, G of n would be, and I think this is just a repeat slide, but basically I want to reiterate that using the number of misplaced tiles, we have pretty good performance. But when we use the goal case where we actually do the sum of misplaced tiles, we get better performance. So that would be a better algorithm, a better path to go. And then so in this case, the best path we need to go, we're doing optimal, would be a little bit longer distance because we have to go all the way down to here and then go around. So this is saying basically the H star for this case was not doing any diagonals. But the best performance is actually going diagonal steps between different things. And then the consistent heuristic definition is the admissible heuristic is consistent or satisfies a monotone restriction of every node n and every successor n prime of n. So it's basically saying if there's a better path that actually goes through multiple steps, that's the path we want to take. So in this case, the path where we have less amount of nodes is better performance. And so in this case, we have the number of misplaced tiles and the sum of distances. Both of these are consistent, since both of these basically we have less nodes to go through different steps. And then finally, the cost, the robot navigation, the cost of the step. So basically what I'm trying to say here is the straight line function is consistent, but it's not the optimal path because we can basically get there the same way, the same amount of points going basically one-dimensional ways. Whereas if we go diagonally in a few instances, we get worse performance. So what it's saying is the h function is consistent, then the function f along with any path is non-decreasing. So basically it's saying h is consistent if the path doesn't get, if the path stays the same after a number of steps. And if h is consistent, then whenever h star expands, a node has already been found at an optimal path. So basically it's saying if it's increasing, we've probably already found another path. There's another path available. And then if the heuristic h is consistent, then let's close be the list of states associated with expanded nodes. So what I'm saying here is basically you want to keep track of the nodes that you've gone through, and if they're consistent, if the performance is getting worse, then discard a node that has a larger longer step function. So what we're trying to do here is basically define how searching works and how to know when to stop your paths from going ahead. And then the complexity of consistent A star, S is the star of the state space, R be the maximum number of states, and then assume that at the time to close the test, state is closed if big O of 0. So there's basically saying there's only one. You don't have to. You basically quit searching when you found the best path, and the time complexity is the size of the state space times the number of stars log of s. So this is a logarithmic times s complexity. And then for the heuristic accuracy, h of n is 0 if all nodes are admissible and consistent. Hence, breadth first and uniform cost are a particular type of A star search. So basically saying all nodes are equally able. With a depth first search, you may not be able to reach all the different nodes, but with an H star, you will. So breadth first and uniform cost are particular A star functions. And if you want to do for the assignment, you've already done breadth first, but if you want to develop a uniform cost search function for the heuristic search, I'm okay with that. And then finally, let H1 and 2 be two admissible and consistent heuristics such as for all nodes of n. So basically what this is saying is both heuristics are good as long as if one's better than the other, use that one, but they can also be the same. And then also, let's say every node is expandable by A star using H2. It can also be expanded using A star. So basically saying these paths are both good. And then to define the iterative deepening A star search, we have a cost function and a heuristic function that's admissible and consistent. So each iteration is depth first, but then cutoff on a value is expand. So it's doing depth first, whereas the other ones were, kind of doing breadth first. So in this case, the number of misplaced tiles plus a step function. So we have a cutoff of 4. So basically it's saying, okay, this is the performance we have right now. When it's consistent, remember, you don't want to make the performance get worse. So we have a 4 here. This one's equal, so we cut this one off. We're not going to go down this path at all. You see this one's 6. Cutoff is still 4. It's 5. Oh, this is not, so it's not going to keep on going further. We got 5. And then we see it's 6. So all these paths are lower than the cutoff. So what we're going to do is now increase the cutoff to 5. See when that's 4. We have a path that's 5. Oh, we have one that's 7, so we don't want to go on that one. That one's 5. That one's 5. And that one's 6. So basically what's happening with the iterative is you have a cutoff value. And maybe you start with the initial score, the f of n score of the function, and then you increase from there until you get a path that gets the goal. And so the iterative is a local procedure. Good heuristics should provide some global look ahead, so at low computational cost. So basically, he's trying to say is you maybe want to have a smart cutoff. Thinking, okay, maybe we will get worse like we do with the maze one. And then there's something called a hill climbing search. Now there exists a successor S for the current state in N, such that the number of states, H of S, so at the current number of states, is less than H of N. So it's basically saying the successor state should have a lower score than the current state you're in. And then S should be less than all the other successors of T of N. And then so we're going to move on from T to N, otherwise halt at N. So basically what the hill climbing search does is it's very similar to the iterative one, where we're looking for successor states that are going to take us to a lower path. And it's similar to the greedy search, but we notice here we don't have a cost function. We're just basically looking for performance states. But this is not a complete function because it will terminate at a local minima, which means some places it might get stuck for a little while where it doesn't get better. Because notice here, it has to get better. And then also has to get better because it's less than, not less than or equal to, or if we put plateaus or ridges. So here's our current state, and basically we're trying to get better, and then we keep on moving up the path. And look here, we might hit a local minima at this particular state, and then we'd get stuck. And so, well, we don't have to calculate a cost function. There is a chance of local maximum plateaus and ridges. And so think about it. How could you get rid of these drawbacks? Generally what we do is when we have things with local minimas, we just basically introduce randomness. So if we get stuck, we'll just restart again, and we'll start with it at a different position or something like that. Or we might just do a random walk where if we get stuck for a little bit, we'll kind of just go down one of the paths, and then hopefully it starts getting better. And again, some problem spaces are great for hill climbing, others are terrible. So with a lot of these algorithms, they're not going to solve every problem, but you can try to tweak them and figure out which ones would be best for a particular problem. And so in my work, we do a lot of trade studies where we'll have maybe 3 or 4 algorithms, and we do basically a bake-off to see which one has the best performance. Excuse me. And so for hill climbing example, we always want this number to keep on going down, so it's going to be the number of tiles out of place. So in this case, we have one of the paths was a -5, so it was getting worse. and then it was going up, and so in this case, it's increasing again. So we have so the reason why we do negative number of tiles out of place, it's hill climbing. So the number should always the h value should always go up. And so let me show you. Notice here, successors. Well, in this case, we're doing now, but basically it should always increase. And so in this case, the value needs to be less than h3. And so in this case, it is h3, but we're just going to go down this plateau, and then see we got one that's 4, so it's less than this one that goes down 2. And then in this case we have 1, and then we're going to go to the goal state, which is 1, 2, 3, 4, 5, 6, 7, 8. But notice here, as long as the value is increasing for h, we're going to keep on going forward. But if we don't basically get stuck in a plateau where stuff kind of stays the same, we may go down the wrong path. And so to give you an example of plateau, all of these are 7. So we have really no path to go down. And so we have a hard time picking. And then some other algorithms we have called steep ascent. It's also called gradient ascent. Basically, we just kind of go down the best path we can until we find the goal. It's very similar to the hill climbing. Similar to annealing. Annealing means kind of we're just adding a little bit of randomness, or kind of make estimations. And there's something called genetic algorithm. Genetic algorithms, basically, we add in randomness as a form of like DNA. So each fact you're looking at is considered DNA, and we randomly mutate them and then see which paths are the best ones. Genetic algorithms use a lot to find which features are best for some feature for face recognition or image matching. And then so we've gone over search techniques, and when do you want to use a search technique? So when the search space is small, it's usually a good time to use a search technique and search space means like the directions, because it's pretty easy to implement, and it probably will find the best path. And then basically you only want to use it when the search space is large, so you have lots of different factors. If you have a heuristic, so you don't really want to do a blind space if you're doing a searching problem. Do blind searches if you do a search problem if your space is very large. But if you know there's a good technique, then you should use it. So we went over in today's is the admissible heuristic and A star algorithm. We went over A star basically is what we consistently went over. The main things you want to focus on is for the programming assignment is I would implement just a basic A star and then an iterative decreasing ADIA star, as those two is for your algorithms for the updated search algorithm. And I hope you enjoyed this lecture. For next week, what we're going to go over is adversarial searches, which it'd be a human pitting against a robot.